So today's video is going to be on continuity of functions in several variables. And so we're going to primarily think about this in 3 dimensions because it's kind of difficult to at least imagine graphically in 4 dimensions or anything beyond that. And so what you kind of want to imagine is like, okay, so we know that continuity, when we're talking about continuity on the real number line, or like functions in a single variable, you're imagining you've got a curve, and that curve is continuous if there's no breaks in the line. That's really the idea, and that actually, it's pretty solid. It's a pretty solid notion, and that's basically how we're thinking about it in 3 dimensions, except for the fact that we're not talking about lines, or maybe we do talk about lines in space, which is fine, curves, for example, but oftentimes we're talking about surfaces. We're talking about entire surfaces, right, okay, where we've got a function z in terms of x and y, we've got an entire surface, and when you have a surface, a discontinuity might look different than just like a single point. Okay, could it be a point? It could be a point. You know, it could be like the point 0, 0, for example, if that ends up having you divide by 0. But oftentimes it could also be something like a curve. Like an entire curve could be, in fact, your discontinuity. And so we want to be able to define that discontinuity. Like say, okay, so here's the issue with the domain. The domain ends up being discontinuous within these bounds or along this curve because we end up doing things like, we end up having the square root of a negative number, we end up dividing by 0, or we end up having the natural log be negative or a non-positive, right? Okay, because we know that the natural log needs to be non-negative. So what we're going to do is we're going to look at like, well, what do you do in that case? And it's actually not that hard to think about. We will take a little look at the definition for continuity, but that's just, just so that we touch the bases when it comes to doing our math, okay? And show that, in fact, it's pretty much the same as it would be in 2 dimensions as well, okay? So let's take a look at that. Let's get started. Okay, so we're going to start out with our definition for continuity. And we've got a function f of xy is continuous at a point AB in its domain if the following conditions are satisfied. So we have f of AB exists, right? That's a requirement. If you remember from Calc 1, you needed that f of AB had to exist. The limit as xy approaches AB of f of xy exists, so we have to also have the limit. And then the limit has to equal the value of the function. So those 3 things are the requirements for continuity, okay? And they are exactly the same, basically, as they are in 2 dimensions, all right? And in fact, if we were even look at 3, 4, 5, what x dimensions, n dimensions, we pretty much get a similar definition of continuity, a very, very similar definition of continuity, and the same basic idea. So let's say, for example, we want to show that we've got f of xy equals 3x plus 2y over x plus y plus 1 is continuous. At, and remember continuity is defined at a point, our AB, at 5, negative 3. Right? Notice as well that rather than at x equals 4, x equals negative 3, or x equals 5, we actually are given a point on the xy plane because our function is in terms of x and y. Same idea that we've been working with. So, 1, we need to show that f of AB exists. Well, you'll note that the bottom, the denominator, will only be undefined when x plus y plus 1 equals 0. That's not going to be the case for 5, negative 3. So we'll just find f of 5, negative 3, which is going to equal 3 times 5 plus 2 times negative 3 over 5 plus negative 3 plus 1. And so that's 15 minus 6 divided by 3, or 9 divided by 3, which equals 3. So check for step 1. Yep, f of AB exists. In fact, we say, actually, let's be more concrete about that. F of 5, negative 3 exists. 2, we need to show that the limit exists. And again, we're going to be able to do this by direct substitution. We've got the limit xy approaches, in this case, and it's going to be 5, negative 3, of 3x plus 2y over x plus y plus 1. We can directly substitute it. And that actually is also going to equal 3. All right, well, we'll do it. We'll do the direct substitution. It'll be 3 times 5 plus 2 times negative 3 divided by 5 plus negative 3 plus 1. Right, because there's no issue at all with solving this by substitution, okay, which equals 3. All right, so the limit exists, and that's our second requirement for continuity. And then 4, we need to have the two of them actually be the same. So we've got the limit as xy approaches 5, -3, okay, of f of xy. Let's just say that's what it is, which equals 3. That also equals f of 5, -3. So condition 3 is also fulfilled. So f of xy is continuous at 5, -3. All right, same thing that we actually have been doing. This one's actually really straightforward because it's all substitution, right? That's for you mathy people out there. We're all mathy people, but you know, for the really mathy people. Now, let's take a look at 3 theorems and go ahead and pause them, read them for a second. I'm going to go over them pretty briefly. They may help us out a little bit later. They are, in fact, things that we've seen before again in Calc 1. They hold over from Calc 1. They're just now working inside of 3 variables, or excuse me, 2 variables, functions of 2 variables. One is that if we add together 2 continuous functions, we get a continuous function, okay? That's the first one. So that might end up coming in pretty handy for us as we do more theorem work. 2, the product of continuous functions is continuous. That is that we can multiply 2 continuous functions together and get another continuous function, okay? And it will still be continuous at the same point. Right? Same point, continuous at the same point. X naught, Y naught. And then also, the composition of continuous functions is continuous as well. Okay? And what we want to do when we take compositions, just be careful when you are connecting your domains and ranges. Right? That your domains and ranges match. Okay? Because like if you think about composition now, what's happening here, and quite literally this is what we're looking at. We've got a, let's say for example, we have, here's our domain. This is the domain of f. All right, so here's the domain of f, and it moves into the range, its range, right? Okay, so we move into the range. So we utilize f in order to move into the range. What we have to be careful about, or be cognizant of, is that we want to make sure that we do, when we do actually go through and compose, all right, the 2 functions here, that we are picking something that is also in. And we can imagine maybe it's a subset, doesn't really matter, but that is also inside of the domain of our function g, right? And then that goes into the range of g. Okay, and there's your range of g. And so basically what ends up happening, like, what'll end up happening, like you just want to make sure that you want to, if you are taking the function from f into its range, you want to make sure that if you want to compose, that you're going to select something that's in the domain of G. Okay, you've got to be able to pick something that actually can be defined in G, right? And that's kind of a requirement. Well, it's definitely a requirement here because it's actually saying that G is a function of 2 variables, okay? And we've got f as a function, all right? And that z naught is in that domain of f, right? And so that's actually a really big requirement. Because, or z naught is in the domain of g, for example, in our case. Because if not, what you're going to end up having is you're going to have a mapping, right, that goes from the domain of f into the range of f, but then, right, if it's not in the domain of g, it ends up being undefined. Okay, and that kind of messes with continuity and all sorts of other things when we start dealing with functions, multivariable functions that possibly have different domains. So we've got these 3 requirements, right? The sum of a continuous function is continuous. The product of a continuous function is continuous. And if you compose 2 continuous functions, and they're composed at points that are in their domains, right? The appropriate domains, and in addition that are continuous at those points, right? Then we actually get continuity back, all right? So make sure that as you're reading the theorem 4.4, that you understand those requirements when it comes to the domains and ranges of your functions. So now to end our brief conversation about continuity, what we want to now do is just look at and determine where an entire function is continuous. So now we've talked about continuity at a point, right? Remember that you now can talk about the continuity of a function on an interval. So let's say, for example, I have this function. I've got f of xy equals the natural log of x plus y. In our conversation about domain, we talked about the fact that x plus y here has got to be strictly greater than 0. Okay? Because if x plus y is not greater than 0, then the function is not defined any longer. And so that's actually kind of going to be that's a really important point. Okay? So we need that, right, that x plus y is greater than 0. That means that x has to be greater than negative y, or let's actually rewrite this and we're going to make it that, that x has to be greater than negative y, or that, y, or negative x is less than y, or that y is less than, or y is greater than negative x, excuse me. Y is greater than negative x. Okay. So y must be greater than negative x. Right, just using some algebra there. That got a little tricky in terms of the signs. Okay, that's why I was thinking about it. And so now I imagine here's my graph, and there's that line y equals negative x. So there's the line. Okay, there's my line, and since y has to be greater than negative x, okay, that means that we're going to end up being above that line. Okay, because y has to be greater than negative x. Right? We can even check that. Like, say, for example, I pick over here. Let's say that that is 3, 1. Okay? So 1 is greater than negative 3. That works. Awesome. That's the one. Okay? And so, hence, this is the domain of that function. Okay? And here is the discontinuity. Okay? The discontinuity here is that x plus y equal to 0. All right, so what we're going to say is the function is continuous for, and we'll write it like something like this, xy belonging to R such that y is greater than negative x. So as long as that holds, we're inside of that entire region, and that's the region in which we have continuity. Okay? And that also kind of defines our domain. Right? It makes sense. So that completes our brief discussion of continuity. Basically, the idea here is that you're looking at something, continuity is this idea of where do we have, like, in this case, holes, lines, cuts inside of our curves, inside of our surfaces, right? And basically, that's where the domain ends up being undefined, right? If you really want to think about it, that's one of the big takeaways from understanding continuity for our purposes right now, right? We want to imagine that we're going to have this smooth surface, right? And when we talk about a smooth surface, that's one where there are no discontinuities, right? And this is going to end up becoming really important inside of later chapters, where we're actually going to have to define things as being smooth. And since they're smooth, it's a surface in which we have continuity along the entirety of the surface, all right? So really brief here. Want to give you this kind of notion of like, oh, we still have continuity inside of calculus and inside of functions of multiple variables or several variables, all right? So this ends the lecture.